Um, there we go. All right. Welcome everyone to another gathering of the Community of Practice in Sustainable Concrete, hosted proudly by SmartCrete CRC. I am Arun. I work for Advanced Precast, and I'll be your host today. Uh, Before we start, the spirit of reconciliation, we acknowledge the traditional custodians of country throughout Australia and their continuing connections to land, sea, and community. We pay our respects to elders past and present and extend that respect uh, to all Aboriginal and Torres Strait Islander peoples today. Smart CRC, as many of you would know by now, brings researchers and industry and government together to turn sustainable concrete research into practical solutions for infrastructure. These sessions that we do are about discussing and sharing those ideas, practical challenges, and exploring what sustainable concrete looks like in the real world. Today's session is on the applications of calcined clay in low carbon concrete. I did think about an opening with a calcined clay joke, but I decided not to get too fired up before the speakers even started. Uh, the background to today's topic is very practical. For a long period of time, low carbon concrete in Australia has heavily relied on materials like fly ash and slag, but as climate change takes over, the coal-fired power stations come to close, and the steelmaking slowly moves away from the traditional blast furnace routes and also away from Australia. The future supply of those familiar supplementary cementitious materials is not something we can take for granted. At the same time, the concrete industry, as we know, still needs materials that are credible, scalable, and also practical enough to use in real projects in large scale. This is where calcined clay becomes an important part of the mixed designs and discussions. Clay is widely available in Australia, but what we don't know is the right type of clay and also the right way to process it. Once we do it that way, it can become a useful low carbon cementitious material for concrete. It is not a magic replacement for everything, but it is one of the more realistic options being explored in the industry. Looks beyond fly ash and slag. The key question is whether it can meet the performance, durability, cost, constructability expectations that we have in the industry and what the asset owners need. Uh, Today's discussion focuses in and around this on a smart grid CRC research collaboration involving Boral and the University of Technology, Sydney. The project is looking at the economic viability, material properties, and sustainability of calcined clay concrete. A few housekeeping uh, before we start. This session is being recorded and will be shared with registered attendees. We kindly ask to keep your microphone off while the presenters are speaking. We'll hear from each speaker in turn and then open the floor for questions. And if you have a question during the presentations, feel free to put it in the chat or hold it for the Q&A. We are fortunate today to have two excellent speakers bringing complementary research and industry perspectives on calcined clay, low carbon binders, and the pathways towards practical adoption. First speaker, Dr. Camille Holt. She completed her PhD in chemistry at University of New South Wales in 2014 before joining Boral's innovation team in 2015. Over the past 11 years or so, she has been involved in the development of concrete products and has contributed to a range of collaborative research projects with universities. Camille is now Innovation Research Manager in Boral's Sustainability and Innovation team, where she leads early stage product development with an emphasis on low carbon binders. She also continues to take part in applied research projects, including the calcined clay project being presented today. Camille, thank you for joining us today. The floor is yours.
Thanks, Arun. I'll just share my screen. All right, obligatory check that everything is all good.
Yeah, perfect. All yours, Camille.
Lovely, and yeah, thank you for the introduction, and yeah, we'll get started. So yeah, as Arun said, my name is Camille, and I'm the Innovation Research Manager and Sustainability Innovation team at Boral. And today, Paul and I are going to be talking about the Smart Creek project that we've been involved with, along with a range of other people investigating an Australian sourced and produced calcined clay. And we thank Smart Creek for the opportunity to share the outcomes of this work with you. So firstly, I'm sure that everyone on this call is going to be familiar with the idea of calcined clay and why it's gaining attention as an SEM. But first of all, start with some context. Concrete is actually an environmentally sustainable building material with a comparatively low embodied carbon content compared to other well-known construction materials such as steel or wood. However, it is due to the sheer amount of concrete that is produced, and there's the often quoted statistic that concrete is the second most used commodity after water. But it's because of the sheer amount of concrete that we make that the CO2 emissions from our industry are significant. And there's an ever-growing body of research which seeks to address this issue. Many avenues through which CO2 emissions could be lowered have been highlighted, and it is only through a multi-pronged approach that we'll be able to reduce the embodied carbon of concrete and other cementitious products enough to meet global reduction targets. And so, as I'm sure many of you will also be familiar with the Global Cement and Concrete Association's roadmap to net zero by 2050. And here you can see all the areas in which we need to target embodied carbon in concrete. And it's interesting to note that in order to get to net zero, over a third of our CO2 reduction is budgeted to come from carbon capture, utilization, and storage. Equally interesting to note is that CCUS technology required to eliminate this massive chunk of CO2 emissions isn't projected to properly take off until well into the next decade. And so this means that we need to focus on the areas where the technology already exists or is more mature. And we can see many examples of that listed on the left-hand side of the slide. But today we are focusing on just one approach. And we all know by now that the largest portion of CO2 emissions associated with concrete come from the cement. And so in Australia, cement production is responsible for about 1% of carbon emissions, which is lower than the global average, which sits somewhere between kind of 5 and 10%, depending on who you ask. And one way that we can reduce the embodied carbon of concrete quickly and easily is simply to reduce the amount of cement in our concrete and replace it with a different reactive material. And so supplementary cementitious materials have been used as cement replacements for many decades in Australia, and their impact on concrete properties is well known. The use of SEMs imparts favourable properties to concrete, aside from lowering the embodied carbon, such as increases in durability. And these, again, are all well known and understood in our industry. But what we also know, as Arun said, was that over time, our two favourite SEMs, slag and fly ash, will increasingly become more difficult to source. With less carbon-intensive steel manufacturing practices and the shift towards renewable energy, this will mean a reduction in the availability of blast furnace slag and fly ash in the future. So there is a need to find another SEM source to bridge the gap and allow us to sustainably continue providing our customers with lower carbon concrete. And there are a plethora of materials which have been studied as partial cement replacements and have been reported in the research literature. Many of these are waste products or byproducts from other processes, which is fantastic for circularity. However, many of these materials can suffer from two key drawbacks. Either they don't allow us to replace a significant enough amount of our cement, or the supply isn't sufficient. Maybe the supply is localized in one geographical area, or the volumes of material available aren't sufficient, or the quality or volume might be variable, and we can't rely on having a stable source. So the question that a company like Boral must ask is which of the available materials are going to allow us to replace enough cement to appreciably reduce the clinker factor of our concrete, while also being available at the scale needed to meet demand for low carbon concrete into the future. And so this is why we're here today talking about calcined clay. It's widely available. It has been well studied in the literature and is proving itself a viable supplement to our current SEMs. And there are significant amounts of kaolinite in Australia, as indicated by the map on the slide, with deposits close to major cities. And so this can minimise the distance that the clay would need to be transported, which is important for cost as well as carbon footprint. And so kaolinite is the clay that we normally tend to talk about, but there are other types of clays. And if we compare the structure of kaolinite with illite and montmorillonite, we'll start to get a feeling why kaolinite is the preferred clay. And so we can see that each are made up of sheets of alumina and silica. But if you have kaolinite on the left-hand side, you can see that it's comprised of one silica sheet for every alumina sheet, whereas illite and montmorillonite have two silica sheets for every alumina sheet. And the alumina is sandwiched between the silica sheets, leaving the aluminium atoms harder to get to, and this makes the clay less reactive. So that's why we tend to focus on kaolinite. It generally produces a more reactive calcined clay. And when you take a clay out of the ground, it's not reactive in its raw form, and so we need to activate it. This is normally done thermally in a process called calcination. So the calcination of clays at high temperature causes dehydroxylation of or loss of water from the clay structure. And this disrupts the crystallinity of the clay and produces a more reactive material. And so for kaolinite, this dehydroxylation can occur at temperatures in the range of 650 to 850 degrees Celsius, which can depend on the equipment being used to calcine the clay, the scale, as well as the properties of the clay. At an industrial scale, calciners can take the form of a traditional rotary kiln, like those used to produce clinker, or a flash calciner. In this project, the flash calciner was used to produce our clay. And whilst calcination does add more processing steps, including treatment at high temperature, kilns are run at about half the temperature used for clinkering. So there is a carbon saving compared to cement. So what happens when we use calcined clay as a cement replacement? Without trying to steal too much of Paul's thunder, when you compare calcined clay to fly ash and slag, the chemistry is highly similar. All three materials are reactive aluminosilicates, which will react in the presence of hydroxides to form the same hydration products. But one notable difference is in the particle shapes. And as you can see here in figure B, metakaolin, so kaolinite, which has been calcined, does tend to have a kind of a flaky plate-like shape, which can impact concrete workability. But the production of clay as an SEM has already been trialled overseas, with pilot scale trials having been conducted in India and Cuba as part of research into the limestone calcined clay cement, or LC3 binder system, which has proved the feasibility of clays as a partial cement replacement. Australian standards are also now beginning to include calcined clay through AS 3582.4, the manufactured pozzolan standard. And whilst calcined clay is starting to gain traction in Australia, we're still in the position of having relatively few examples of local production and use. So therefore, the purpose of this project has been to produce a calcined clay from an Australian source and test it to verify the feasibility of calcining clay in Australia for use in concrete. And this project has brought together several stakeholders, ranging from materials producers, academia, and end users, as we're all important pieces of the puzzle. Boral, as a provider of construction materials, Transport for New South Wales, who use a lot of concrete and often technically demanding projects, Calix, who contributed their expertise in flash calcination, and UTS, who is our partner university, bringing specialist knowledge and access to research facilities. So Boral has partnered with UTS for a good number of years now, with the Boral UTS Centre for Sustainable Building, which was established in 2020. And since then, we've continued to benefit from the ongoing relationship which has been developed. And it's been great working with Paul, Arno, Mark, and the team of terrific postdocs, Stu, Sanket, and Waleed on this project. And I'm now going to pass over to Paul. He's going to present some more details of the research that has been conducted during this project. Thank you.
Thanks a lot, Camille. That's a great presentation and a great start to the problem statement of what calcined clay is, and you can easily see how many people need to come together and collaborate before we even get something on ground, and the way industry is as now. And another partner in this great endeavor is Paul. Dr. Paul Thomas is a senior lecturer in the School of Civil Engineering civil and environmental engineering at the University of Technology, Sydney. His research focuses on the durability and characterization of cement-based construction materials, including alkali silica reaction, delayed etching gate formation, supplementary cementitious materials, and low carbon binders. Paul is the UTS research lead for the Smart Grid CRC project on applications of calcined clay in low carbon concrete, working with Boral Transport for New South Wales and Calix, as Camille mentioned, to assess the viability and durability and sustainability of Australian calcined clay for a low carbon concrete binder. He brings the research and the testing perspectives today, particularly around how calcined clay systems can be evaluated with enough confidence for broader industry adoption. Paul, thank you for joining with us today, and you are joining us from an airport lounge as you are traveling around. As pure academic style, just get to do a presentation or read a paper in between your transits. So great to have you here. Over to you. We have you on mute, Paul.
Sorry, I went to share screen before.
Yeah, all right.
So can you see?
Yes, we can see the
Okay,
screen.
okay, you're good,
All right.
good. I did take myself off mute, but it went back on for some reason.
All
No, thank you, Arun, and thanks, Camille, for setting this up. And of course, stealing all my thunder, talking about the structure of clays. So I'm going to definitely avoid that. I mean, basically, that's the aim of the project was really to have a look at the feasibility of calcined clays as a substitute for other supplementary cementitious materials. So if I can just get through this. And I mean, obviously, the argument is that cement has a high embodied carbon, and STMs are a possible way to reduce that embodied carbon. And really, I've got here the 2050 zero emissions target rather than the 2031, but it's the 2031, the 43% of 2005 levels that we're really targeting here, because we're simply substituting cement. As Camille put out in one of the diagrams, that basically there's still a lot of emissions that need to be addressed. So this is the first step along the way. So basically, and she also commented on the fact that our major SDMs are fly ash and granulated blast furnace slag. But of course, recently we've had the publication of the new standard of SDMs of manufactured pozzolans, which is now being introduced into other standards as well, which is really important, that 5100.5, 3600, and also the state transport authorities utilize and incorporate standards for manufactured pozzolans in their specifications, because otherwise the material cannot be used because it doesn't filter through the specifications. So that's really important. Camille mentioned, had a bit quick talk about the limiting supply of fly ash and GGBFS, and also possibly the quality as well. And of course, a lot of people are talking about mining pond ash as a possibility, or importing ash for fly ash. Problems there, of course, means you've got variability in quality, but also you're actually, by processing the materials, you're starting to put embodied carbon back in. Similarly, with blast furnace slag, in Australia, we actually only manufacture about a third of our consumptions. We import 2/3 of the blast furnace slag consumed in Australia. So it's already, to some extent, an issue. Of course, blast furnace slag is not really, so calcined clay or fly ash are not really substitutes for blast furnace slag, particularly in the role that blast furnace slag has. And that's particularly in chloride resistance in marine environments. So one of the things that we've been looking at is looking at calcined clay really as a substitute for fly ash. And of course, one of the reasons, and Camille mentioned this, one of the reasons why we're interested in calcined clay is because it's widely available. And there's a large supply of suitable and importantly low-grade kaolinitic clays which can be used for this purpose. We do have to put some energy in. We do need to calcine it. We need to dehydroxylate. We need to activate it in order to make it a pozzolan. However, the temperatures are relatively low. I've actually got 600 to 800 here. Camille had 650 to 850. It's somewhere in between there that you need to calcine it. But these are the sort of temperatures you can calcine using electric furnaces. In our case, a flat calciner. But if you're using electric furnaces, you can use renewable energies, and that brings the embodied carbon down to very close to zero. Then it becomes a transport issue rather than a fossil fuels issue. As Camille pointed out, there's plenty of calcined of kaolinite clay around the world, and it's also available in all the major population centres around Australia as well. So there's the point of this is that there's a potential for an economic supply of calcined clay for bulk quantity. So the millions of tons that are required in the construction industry. As far as the current status of calcined clay goes, Camille did mention this a little bit as well. Worldwide, there is production at scale. There are a number of plants around the world. There's a half-ton plant being built in Colombia. There's another one in France. There's a number of plants being built in West Africa. And these plants are marketing products. So they're using the materials in a commercial sense. So it's gone to a stage beyond where we are at in Australia, whereas we're really at a research scale, although there are some small production facilities in the kiloton PA around, or in Victoria, essentially. So my part really is about looking at the development of the material. And the way we looked at it was not as an LC3 type material, but rather as a material as a pozzolan to substitute. It's an aluminosilicate, and it's as a direct replacement for fly ash. If we're going to use the material, it has to have suitable hardened properties. So roughly speaking, the strength needs to be comparable or better if it's superior to fly ash blended cements. And a whole bunch of other hardened properties, so shrinkage, creep, modulus, tensile strength, and so on. The durability also needs to be comparable to, we're going to take fly ash as this reference. Again, it needs to be comparable. Fly ash is not particularly resistant to chloride. So we might not expect calcined clay to either. The carbonation resistance is probably not too good as well for fly ash. So if we do better than fly ash, then again, we're on to a winner. And again, what fly ash is really good at is mitigation of ASR. And so we need to address that with calcined clay. So I'm going to have a quick look at some strength and shrinkage and carbonation and ASR data. I'll also have a look, and this is the main problem, and Camille did broach a little bit on this problem, and that is the fresh properties of concretes containing calcined clay are deteriorating a little bit. So we need to achieve suitable workability, and we also need to retain that workability as the materials are transported from batching plants to construction sites. So first of all, this is the material that we used. We had a calcined clay, which is roughly 48% kaolinite. It was flash calcined by Calix in their Batman flash calciner. And it produced a metakaolin. And you can see from the XRD here that we have metakaolin. We haven't dehydroxylated the illite, so it gives you an idea of the temperature. And we certainly haven't produced any mullite in this process to depassivate the material. So no recrystallization is occurring. So this is a reactive material. In our program, we had we're using the calcined clay as a replacement for fly ash. So we had a binary and a ternary blend. The binary blend is a 70-30 fly ash blend, which is replicated in the calcined clays. And the ternary blends were blast furnace slag blends with fly ash, again, where the fly ash is substituted in with the calcined clay. We had a look at two possibilities for replacing the fly ash. We initially replaced it by volume. Of course, calcined clay is more dense than fly ash. And so we needed to incorporate a higher mass in order to replicate the volume substitution. We found that really this is a bit over substituting, and the workability did deteriorate a little bit too much. On a mass basis, it worked very well. We also had a look at ternary blends where we partially replaced the fly ash. And actually that was replicated as well in the ternary blend with blast furnace slag, where we also 50-50 substituted the fly ash in that ternary blend. So that was, this is after a lot of work in developing and working out how to get the workability right and what sort of admixtures to use. So we ended up with these 5 mixtures, and the aim was to really produce a grade 32 megapascal concrete for pavement in a field trial. From a workability perspective, let me just scroll through these things. Of course, the water demand of calcined clay is a little bit higher than that of fly ash, so we needed to put greater content of high-range water reducer in, and that was both for the fly ash blends as well as the ternary blends with blast furnace slag. If you do the admixture right, you actually get to a point where you can actually retain, you can get all of the workability right, and you can retain the workability as well. So here's some examples. This is the 32. This is the calcined clay substituted blend, very comparable workability retention. And similarly for the blast furnace slag, very good workability retention. Now for some of the hardened properties, we were looking at, we made a 32 megapascal grade. So we easily reached the 32 megapascal grade. In fact, the calcined clay blends produced higher strength than the fly ash blends. They also produce better early age strength than the fly ash blends for both the blast furnace and the binary fly ash substitution blends. So from a strength basis, we had really good results. The other thing I'm going to report here is drying shrinkage. Well, all of our mixes were well within the 1,000 microstrain limit. So all of them passed. This is essentially an R53 type mix. Of course, the workability because of the water demand, the workability of the calcined clay beds was shrinkage. The shrinkage of the calcined clay was slightly greater because of the higher water demand in the system. And that was true for both systems, a bit less so for the blast furnace slag system. And of course, we did succeed in making suitable concrete for placement. And this is an example of a successful pour. And you can see that we're pumping the concrete. It has good workability. And it was placed. It was very easy to place and finish. So it's very easy to get the fresh properties right with the right admixtures. We also went back and had a look, and essentially, even though slightly higher drying shrinkage, there's no cracking in the calcined clay bed. So again, if you get the workability right, you have very concrete where the drying shrinkage is low enough, so there's no cracking. This is another view, slightly further out. The dots are about a meter apart, just to give you an idea of the scale. We have done a little bit on durability. We haven't completed the chloride test, so I'm not going to present those today. But from a carbonation perspective, carbonation at 56 days is slightly better than fly ash. For the binary blends, for the ternary blends, again, the carbonation depth is slightly better. So it's more resistant to carbonation. From a durability perspective, we've done some AMBT. This is a reactive aggregate, and I'm sure you can see that this reactive aggregate is extremely reactive. It's above 0.1 at 10 days, and it's above 0.3 at 21 days. Whereas we got two blends down here, a fly ash and a slag blend for comparison, and you can see that they parallel each other. I think it takes around 91 days before they get to 0.1. This is part of that new standard AS 1141.60.3 using blended cements in mitigation of ASR. And the calcined clay, this particular calcined clay is slightly less good than the fly ash, so we needed 30% substitution rather than 25% for the fly ash. But essentially, both fly ash and calcined clay are excellent in mitigating ASR. And that basically brings me to an end. I mean, basically, so yeah, one of the aims of this is to test the feasibility, as there is a belief that the traditional SCMs will be constrained supply with increasing demand or reduced supply because of the closure of power stations. And calcined clay shows a lot of promise because you can get suitable strength, suitable workability, and you can produce durable materials. Calcined clays are widespread, so there's no problem with niche material. We're not talking about a sprinkling of clays. We're not talking about small volumes available. So it could fit. It has the excellent potential for a bulk commodity SDM. I'm just going to thank our partners. UTS, of course, has supported the work and helped us get the project together. But the major partners are Smart Creek, who coordinated all of this, but Boral, Transport for New South Wales, and Calex, who made the project possible. So thank you for your time.
Thank you so much, Paul. That's an excellent presentation, and we really appreciate it doing it from the airport, even though you have a nice UTS background on your screen. Yeah. And I think if you have any questions, feel free to put it in the chat. But okay, we have Liam with raised his hand. Liam, do you want to go first? You're on mute.
Right, thank you. It's a question for Paul. In the admixtures you're using in the concrete, without naming brands or anything, were you increasing the amount or were you changing the type? I'm particularly thinking of the work being done in Europe at Technical University of Munich and at EMPA on amphoteric superplasticizers designed for LC3 cements.
You're on mute, Paul.
Sorry, we use the same type for all of our blends. We use the high range water reducer. We also use materials which were available in Australia because we needed to do a field. Our aim was to do a field trial and to make our mix designs for that purpose. We trialed a lot of water reducers and a lot of admixture systems, and actually we found that the European admixtures didn't do any better than the available admixtures in Australia.
Interesting.
Thank you.
We do have another question in the chat. All other things equal, will a 70% GP, 30% calcined clay mix have a lower carbon intensity than a 70% GP and 30% fly ash mix? Just thinking about transport, extracting raw materials, processing, etc.
Was that the calcined clay blend has a lower embodied carbon than the fly ash? Yeah. It really depends on how you where you get your energy from.
Yeah.
So if you get your energy from renewable energy, then calcined clay is the same as fly ash. You still got to process to a certain extent. You still got to transport to a certain extent. But it really, if you're using electricity which comes from fossil fuel based, then the embodied carbon goes way up.
Yeah. And, we have Michael has his hands up, hands raised. Michael, yeah, go for it.
Thanks, Arun, and thanks, Paul and Camille. Paul, hope you're doing well. Just a quick question on the exothermic heat generation for this material versus fly ash, particularly in thicker sections, precast, steam curing, large bridge elements. Just be interested if there's been any mapping of the thermal performance of calcined clay in those applications. Seem to be doing more and more thicker sections.
The answer is, so hello, Michael. Good to see you. The answer to that is no, we haven't done that work. However, if you do the calorimetry of paste and mortars with equivalent substitution levels, they're actually they're fairly similar. I mean, sometimes you have a sulfate imbalance if you overload with calcined clay, but really there's no increase. There's a slight acceleration, but really there's very little difference between the two. Admixtures do make a difference, however. Admixtures can retard the hydration. So if you do need to put a lot of admixture in, then you get a little bit of a retardation, and that actually reduces the heat.
Thanks, Paul. My only follow-on is the surface area of the material. Do you have a big difference in surface area between the two in terms of area for reaction?
Yes, because the calcined clay is higher, and it's simply it's a couple of these. The particles can be smaller, but fly ash is a glassy substance which is spherical, and it's not quite geometrical, but it has a fairly low, relatively speaking, a lower surface area.
Thanks, Paul.
Thanks, Michael. Thanks, Paul. There's another question in the chat. What is the market capacity and development timeline for scaling this? And when could we expect to see opportunities for project level trials? And from Charles, I would like to extend this question from my end to see, I think we have seen years and years of geopolymer was tried and tried in the industry as well. And it took like 20-25 years. And we don't even have a standard put out yet to even scope it. And how do you think the calcined clay / LC3 get in our market? Maybe to Camille and
no problems. In terms of market capacity, like Paul said, we're probably considering, calcined clay maybe it's like a fly ash supplement as a supplement to existing SEMs. So that kind of gives you an idea, I guess, of possible capacity. But all these things, they're going to scale up. You're going to start small, and in terms of project level trials and scaling, it's kind of a chicken egg kind of question, because we want to be able to generate interest in calcined clay, but we can't do that without without material to do trials with customers. And we can't, and sometimes it's hard to get our hands on materials unless there's significant pull from customers. So it's kind of trying to influence people, but yeah, it's going to take a while. Which is why it's important to be doing this kind of work now, so that as we see changes in the availability of existing SEMs, we've already done all the testing. We've already started to look at how we can build capacity to produce the material. So it's not going to be tomorrow, but it's going to be it's on the horizon, and it's hard to say exactly to how many years before we're all just selling calcined clay concrete as as an off-the-shelf product.
Thanks for that, Camille. And there's this question: what was the source of the clay that was used in the present study? And I understand as part of it is confidential, and if you don't want to answer,
It was sourced in New South Wales, and that's about all I can say.
That's all right.
Yeah.
The question from Mick is, hi Paul, can you give us a little more detail on the 32 MPa field trial? What was the application? And I think it's a payment based. Was it structural or non-structural? What was the percentage of calcined clay used?
It was a 30% calcined clay. So we made mixes based on the mix designs that I presented. We made 5 mix designs. We didn't do substitution by volume because the workability wasn't enough. But the aim of the project was to test this as the feasibility of this as a real material, as a real viable SCM, and so we wanted to go all out, and it was structural pavement and reinforced pavement, and we made direct parallels of the fly ash references, and they performed better than the fly ash pavement, than the fly ash equivalents. They're about the same. I mean, it's very anecdotal. We have one mix, and we're doing it in one mix of each blend in an agi track. So, Camille, would you like to add anything to that?
No, I think you've covered it all. Yeah, it was just concrete poured as a slab at a Boral site.
Tristan had a more of a comment in the chat. Sounds like this is not necessarily a low carbon product than fly ash, but more of a response to the declining availability of fly ash. Is that a fair takeaway? And yeah, I would think there's between fly ash and slag there's a duopoly kind of solutions, whereas more solutions will democratize the market to pick any alternative around supplementary cementitious material. Would you like to add anything, Camille or Paul?
No, I do think that for Boral, being able to produce lower carbon concrete is important for us, and it's important for our customers, and so yeah, it is a way of safeguarding our capability to be able to keep producing lower carbon concrete.
Liam, you have your hands
yes.
raised.
My question's about curing. It strikes me that the calcined clay is a better water retaining material than fly ash for obvious reasons, because you get interstitial moisture in the system. In your testing work, I've assumed you've cured it as per AS 1012.9 or 1012.8, which raises an issue about correlating research from Europe to Australia, because in Europe they use plain water instead of lime water. And it strikes me that that could have a significant influence on the pozzolanic reaction of the clay. But also in terms of curing under non-immersion conditions, so curing in situ in the real world, where the effect of superior water retention, and my experiences from dry mix mortar and floor toppings of those materials, is better than something like a fly ash. So the question then becomes is, in situ strengths versus laboratory cured strengths. Have you got an opinion on that?
Definitely, you can make stronger concrete in the laboratory. It's just the way it is. Yeah. What you're trying to do is you try to make that correlation that when you are in the field, you have, and particularly if you're making large patches, then you do have more variability in the material. You have to deal with weather conditions. The day that we poured the concrete, it was 38 degrees or 37 degrees. It was windy and it was dry. So it was a really difficult environment. However, we managed to pour all 5 concretes, and the calcined clay one was excellent. Strength-wise, they all met the R30, but they were all weaker than the laboratory equivalent.
Yes. I'd be very interested to see down the line some cores taken from those slabs to see how they compared.
We would like to do that. We'd also like to do some carbonation studies on them as well, on those cores.
Thank you.
There's a few more questions in the chat, and there's one from Isong Mayo. So just wondering, as the iron and steel industry decarbonizes and more electric arc furnaces come online, do you think EAF slag could be used for cement production in the future? I think it's a bit of a sidebar to the calcined clay, but Camille, do you want to have a take on this?
The biggest issue to overcome with EAF is the oxides, the magnesium and calcium oxides, which can cause unsoundness. So that's probably the first hurdle to overcome, is to make those more viable. Which I'm sure you can do just by changing the manufacturing process, but that would be something you'd have to do with EAF, with steel producers.
Dean Chapman asked, is calcined clay concrete recyclable like every other concrete at the end of its useful life?
I don't think it would be any less recyclable than than concrete with an equivalent amount of SEMs. They're chemically quite similar.
I think we are in the process of building, and maybe in a few years we can smash it down and see how reactive it is on the recycle level. A question from Lisha Dong is, thank you for the presentation. I cannot find the information related to manufactured pozzolans like calcined clay in 3582.4. Would you please clarify?
Is it just not being able to find the standard itself, or?
Yeah, probably not clear, but if you can give an overarching idea of how AS 3582.4 works, that would be good for the audience, Camille.
Okay, it clarifies properties of what the standard considers a manufactured pozzolan, what we can actually use in cement, or like as a cement replacement in our concrete.
And I think the point one looks at fly ash and point two looks at slag, and then it opens up to every other.
Silica fume is number 3.
Yeah.
Because I put all the information into Google, and Google says that atom doesn't match any documents or any. I just cannot find any information about it. If possible, would you please send the description of the whole atom into the chat? Thanks.
Because the standards Australia would not allow to transfer the documents, Australian standards, without there's what's the word? There's copyright. There's copyright issues around transferring, but you can find the documents in internet, and that's probably the same.
No. I don't want the document. I just want that specific information, not the whole document. Just that the information, not the whole document.
All right. I think we'll try to take this request off, and
okay. Thank you. Someone sent to me. Thanks.
All right. No worries. And Michael, you had
thank you. I was just going to add some detail. I was involved in the writing of 3582.4, and what it was intended to be was for manufactured pozzolans and the use of manufactured pozzolans, as opposed to what Camille was saying, fly ash, slag and silica fume, or what's called amorphous silica. So there have been a number of products that have come as considered manufactured pozzolans, and they were tested as part of the development of that standard. And the standard does say that there will be additional ones that will come in the future, but they would have to be addressed as a manufactured pozzolan in accordance with the standard approach that's been developed. So that while there may not be specifics on calcined clay in detail, that's because it was going through, as we all know, an LC3 development with Karen Scrivener and others. And so, yeah, it may not be, Camille, right up to date with calcined clays, but it recognises that manufactured pozzolans is an ongoing SCM that we'll be relying on more and more. So I just wanted to add that comment.
Yeah, thanks for that, Michael. That really clears it up. And Liam, you have your hands on.
It's just an observation about standards in the budget. Australian standards have now been made free if it's compulsory in your work. I'm a partner in a concrete testing company, and we've already been advised by SAI Global that our concessions are coming through. So Standards Australia has not let the grass grow under their feet. They're already enacting that so it's a good news, right?
Yes.
It's always been a bugbear because the public pays for it, and then you have to pay a lot of money to get a copy of the standards. So it's worth people going in the next months to see what they can get. It's likely they'll be able to get it free if it's required for their business.
That's a good information. Thanks for sharing that, Liam. Everything else going on in the budget, it's really slipped through. Let's put it that way. And I think I come from a precast, so I probably use this to ask a couple of questions. Because I think one of the main reality of precast is, especially with the constructability of a precast product, is to be able to lift the panel the next morning. If we pour it today, so if we free up the bed, so we can pour the panel next day, and then the dance goes on, the music goes on. So the early age trend is an extremely important one for us, especially in accordance with the lifting design. And that is probably the biggest barrier of precast products for adapting low carbon concrete in precast products. And how do calcined clay concrete, or LC3, works on early age strength, and is there some interesting work that's been happening at the back end?
Just to point out, we've been working on calcined clay as pozzolan rather than LC3. LC3 has a large portion of limestone in it, and so its properties will be different. The calcined clay materials that we produce tend to have fairly good early age strength. So they're better than blast furnace slag mixers at the same substitution levels, and they're also better than fly ash mixers. So, I mean, if you're talking about heat curing, we haven't done it, so we don't know directly from our experience what the outcome would be, but we would expect reasonable early on strength. I don't know if you're going to get 25 megapascals in 24 hours at 70 degrees. But it would be nice if we could. Well, I mean, we could always we could have a go. I'd like to have a go, actually, if we're interested.
Yeah, I think. Yeah, we like, the thumb rule is to have between 15 to 20 MPa within, let's say, 16-17 hours before we're able to lift the panels. Yeah, Liam, you have your hands raised.
You're
on mute, Liam.
I work in rapid repair for airports and concretes is my primary area of work, and you can achieve 25 MPa in 2 hours.
Yeah.
Australia is actually quite good in that. I'll look you up. There's ways of doing that. Precast is one of the huge industry. Switzerland in particular is now doing a lot of that kind of precast based on CSA, OPC cement blends for tunnelling work.
Yep.
The only criteria being that you don't use steel reinforcement. They use polymeric fibres.
Yeah. And
you can get very, very low chloride iron permeability, down around less than 3 times 10 to the minus 12 millimeters squared per second, or whatever it is.
Thank you for that, Liam.
Yeah.
Another question on the chat is, thank Wakab Adil. Thank you for such an amazing presentation. Just wondering if this research covered only replacement of fly ash OPC to calcined clay, or will it be extended? And if so, what may be explored in the future? And also, considering practical applications, there are any limitations in use of calcined clay in concrete? between Paul and Camille.
Okay. Oh, okay. So in terms of is the work going to be extended? Unfortunately, our project's coming to an end, which is really sad. So there's no further scope in the project to extend the research just yet. But in terms of practical applications, other limitations, not that I'm aware of at the moment.
And do you see a upper limit to the amount of calcined clay being used in concrete? Is 30%?
It's going to depend on the clay source. Different clay sources are going to have different properties as they are, as the mineralogy is going to change. Generally, the higher the kaolinite content, the more difficult it is to increase the cement replacement level. But again, it depends on the clay source.
Good.
There's definitely a limit to the amount of calcined clay they could put in there. So in LC3s, basically the best LC3s are around 50% substitution in total. So that includes 15% limestone. So in other words, 30%.
Yeah, thanks for that. I think we'll take one last question, which is a bit of technical question, and you both have really strong technical backgrounds. And since the pozzolanic reaction consumes calcium hydroxide and drops the pH, is there a risk of introducing carbonation corrosion? What is the replacement threshold limit that we should not increase beyond? I think it's following up on what we discussed, but with the carbonation focus. Paul?
Absolutely. Like fly ash, there is an issue with carbonation. From the work that we've done, we have more carbonation resistance than fly ash blends. So, and again, it depends on where you're using this material. So one of the ways of controlling carbonation is if carbonation is a worry, then addressing the water binder ratio. Reduce the water binder ratio, you reduce the rate of carbonation. And effectively, you can get it down to a PC or a GP level of carbonation if you have a low water binder ratio. So that's the way of addressing carbonation in concrete. But definitely, the fact that you're substituting cement, you're reducing the amount of CH by substituting the cement. And on top of that, you have the pozzolanic reaction. You affect the amount of available CH in two ways. And so that makes any blended cement more susceptible to carbonation. And it doesn't really matter which one it is, whether it's fly ash, slag, blast furnace, fly ash, blast furnace, slag, calcined clay, and so on.
It comes down to having appropriate cover for the concrete that you're using.
Yeah, I agree. I mean, if end of the day is if you have reasonable allowance in the cover, you'd probably be that will solve some of the issues with the corrosion as well. And I think with that note, we can bring this session to a close, except for Wood, who has his hands raised in the last moment. We cannot refuse you, Wood. So
yeah, I think on the question of carbonation, I can't help but to let everyone know that with the I guess with the use of low carbon concrete, increasing use of low carbon concrete, work are being done, which basically indicated that we do need to increase the cover content, the cover requirement in exposure A2 in particular. So I just want to update everyone that the Australian Standard 3600, which is being released for public comment. Please look at it closely because we have basically do two things. One is to separate the exposure A1 and A2 clearly. A1 for internal application and A2 for external application. And in the case of A2, we have recommended increased cover to basically prevent the carbonation-induced corrosion with the use of low carbon concrete. So please pay attention to that. And the draft standard is being released for public comment now.
Thanks for that, Wood. And Michael,
sorry to jump in. It's just Voot had
right.
something to say, so I wanted to add something, Voot, about curing, particularly with low carbon concretes. When you start to increase your SCMs higher and higher, you're going to have to do good curing, or you're not going to get the quality of cover you think you're getting. So that's just a comment. I think that's really important that we follow that curing regime, and what we've used previously may not be good enough, is what I'm getting to, or extended levels of curing. So not by just doing a one-to-one swap, Camille, but if we push higher and higher into the SCMs, it's just is my position. Thanks.
Thanks, Michael. Winter months are here and it's pouring down in Melbourne in rain, and that's curing is a good place to leave and end the conversation. So thank you, Camille and Paul, for sharing your insights with us today, and thank you for everyone for being a wonderful part of this discussion. Really good chat, and this is how we want to run the SmartCrete CRC community of practice, with a lot of discussions and back and forth. And it highlights that low carbon concrete is not only about replacing cement and whatever material is available. It is about understanding supply, processing, reactivity, durability, economics, and the evidence needed for adoption ultimately into the standards. Calcined clay is a strong example why collaboration, like in this project, across the board, Boral, Transport New South Wales, UTS, Calix, across everyone to get this into the market. The technical promise is important. The real value comes with the promise, and hopefully can be converted into reliable specifications and project-ready concrete. And for any follow-up questions or collaboration opportunities, please reach out to SmartCrete CRC. They will help you connect with the right people. And until we see you in the next community of practice, this is thank you from SmartCrete.
Thank you very much.
Take care.
Thank you. Well done.
Thank you, everyone.
Thank you.